Hello, my name is Brian Lee, and this is a video report for Lab 1 in Week 4 of Principles of Physics. To start with, the mission statement of the lab is to observe constant velocity without changing direction, so we have an object under a constant net force of magnitude 0. Additionally, the movement must be one-dimensional. In this scenario, we will observe an object rolling across a flat surface, and, while many people might have used a dry erase marker, since our table had one, we used a frictionless cart as our system, with the surroundings being everything else, including the track. We will come to see that a computational model that takes in only an initial position and an average velocity can be used to predict the motion of this object, given that the surroundings will allow for nearly constant motion. As for relevant formulas, we have velocity update from Newton's second law of motion, which is v equals v naught plus f net divided by m multiplied by delta t, and position update using average velocity, which is r equals r naught plus v average times delta t. This could be written using the kinematic equation for position shown to the right, but since net force will be 0, the last term of that equation will simplify to 0, leaving r naught plus v naught times delta t, and with a net force of 0 and constant velocity, v naught is equal to v average in this case, with v average being v final minus v initial divided by t final minus t initial. Note that since the movement is one-directional, we can replace the position, velocity, and net force vectors with the scalars x, vx, and the x component of net force respectively. Here's a screenshot of the tracker program that was used for the experiment. As you can see, I've set the origin to be roughly in the middle of the video, with positive x pointing towards the right. After giving the cart a push to the left or the negative x direction, positions were recorded frame by frame, beginning with time at t equals 1/3 seconds all the way to 1.2 seconds in mostly 1/3 second increments, except for the last few positions. R naught or R initial is 0.261 meters, and R final is negative 0.341 meters. Afterwards, a computational model using GlowScript to predict the motion of the cart was run, resulting in these figures. In green is the model's data, and in red is the experimental data. A position versus time graph compares the two datasets, while the velocity versus time graph only shows the model's data with constant velocity roughly negative 0.695 meters per second. The underlying code is shown to the left, specifically the while loop, in which the velocity and position of the blue ball, representing the cart, are updated according to the formulas mentioned previously. Although I use a kinematic equation in this case since it makes it easier to manipulate the force vector given by the starter code, and with a force of magnitude 0, that term won't really matter anyways. I set the initial position as 0.261 meters, just like in the experiment, and when defining the velocity, I set it as negative 0.341 minus 0.261, or negative 0.602, divided by 1.2 minus 1/3, which means that the velocity of the object is the average velocity of the cart found in the experiment, and the mass is 0.5 kilograms, even though it's not really used. All in all, the two datasets line up pretty well. Since the model's velocity is taken from the experimental average velocity, we know that the endpoints of the curves would line up perfectly regardless, resulting in a straight line for the predicted data and a non-straight line in reality. Possible reasons, apart from the fact that the net force wouldn't be 0 in real life, include a crooked camera that makes it harder to accurately gauge a consistent point on the cart, and straight-up human error, in that I might not have always chosen the exact spot I should have. In conclusion, I'd say that the computational model accurately predicted the motion of the frictionless cart. I'd even argue that these predictions are even closer than that of experiments using a marker, due to the nature of the frictionless cart and track making the net force as close to 0 as possible. Of course, this was the case for these circumstances, but what about different initial conditions? What if, for example, the orientation of the x-axis was flipped, such that positive is negative and vice versa? Well, the magnitudes of the scalars would be the same, while the signs were flipped, so essentially they're only pointing in the opposite direction now. Otherwise, not much else has changed. Ultimately, although the net force is 0, the forces that constitute the net force I'd say are hard to quantify. We just know that they sum to a magnitude of 0, but we can assume that friction and air resistance are involved.